This is a carbonic compound tutorial presented by the SHLTV with reference Cambridge International AS Chemistry by Laurie Ryan and Roger Norris. So we start with this tutorial by giving the learning outcome. So let's see the learning outcome. You should be able to describe the formation of aldehydes and ketones from oxidation of primary and secondary alcohol. As you can see, you're going to see that the reduction of aldehyde and ketone by using sodium tetraborohydrate and tetrahydroborate, and we have lithium aluminum tetrahydrate. So the next one, we have the reaction of aldehydes and ketone with HCN, so and sodium cyanide, so hydrate. So we have the next one. We have describe the mechanism of nucleophilic addition reaction of hydrogen cyanide. You have described the detection of carbonyl compounds by the use of 2,4-dinitrophenylhydrazine reagent. You have distinguished the between aldehydes and ketone. You have described the formation of that. You have deduced the presence of this group, and then you have analyzed the compound with infrared spectroscopy. So now let's start. So we need to know that when visualizing aldehydes and ketones, we need to first start with a homologous series of aldehydes and ketones, and we have already defined what's a homologous series in the previous tutorials in the introduction of organic chemistry. But now we need to know that aldehydes is one homologous series that has a functional group of a CHO. So the functional group for aldehyde is CHO, and it has a carbonyl functional group. And also this one, the ketone, also have a carbonyl functional group. But the distinction between this one, this aldehyde, and this ketone is that there is going to be one hydrogen bond. There is going to be one hydrogen atom that is going to be added to the carbonyl functional group for aldehydes, while the ketone is instead going to be have two alkyl groups that are attached. Here you have one alkyl group and one hydrogen atom attached to the carbon atom, and here you have two alkyl groups. So now let's see the naming of the structure. You need to know that here when you have only one carbon atom, the carbonyl the compound is going to be called methanol. 2 carbon atom for aldehyde is ethanol, for 3 is propanol, 4 butanol, 5 pentanol. In cases of ketones, when you have ketones only start from 3 carbon atoms, because you realize that for it to have 2 alkyl groups that is going to be attached to the carbon atom of the carbonyl functional group, you need to have 2 carbon atoms which are attached on this side and 1 carbon atom at the center. So it makes a total of 3 carbon atoms. That's why ketone starts from carbon 3, and carbon 3 on ketone is named as propanol, then 4 carbon is butanol, then 5 carbon is penta, 2 on R or penta 3 on, depending on the direction or where the carbonyl functional group is present. So now let's visualize the preparation of aldehydes and ketones. So now the main source of aldehydes and ketones is the oxidation of primary alcohols. So now we need to know that in cases of aldehydes, the preparation of aldehydes is going to be via the oxidation of primary alcohol, while the preparation of ketone is going to be via the oxidation of secondary alcohol. But now the thing that I want to put in mind is that this oxidation is going to be partial oxidation. There are going to be 2 oxidations that occur normally on primary alcohol. You have a partial and you have a full oxidation. Partial oxidation is going to be by the use of the reagent called potassium dichromate. Potassium dichromate only gives a partial oxidation. Now full high oxidation is going to be given by acidified potassium permanganate, and also partial oxidation can also be given by alkalinified instead potassium permanganate or acidified potassium dichromate. So now let's see oxidation of primary alcohol, actually a partial oxidation of primary alcohol. In order to do this, we use acidified potassium dichromate, or you can use also alkalinified potassium permanganate. So this is a mixture. Here you are going to have ethanol and acidified potassium permanganate. All of them are going to add up. So it's going to oxidize it to produce ethanol. So you reflux such that all the ethanol is going to come back going to be reacting again, going up, coming back. All the vaporized ethanol is going to be coming back down, and now ethanol that is going to be produced and is going to move out of the mixture is now going to be collected down here. So that's ethanol. So now these are the different things to visualize here. So, and this, you need to know that what when the reaction is going to occur, you are going to realize that the orange solution the orange solution of potassium permanganate is going to convert green, because potassium dichromate, which is orange and is present in the reagent, is going to be converted to the product of chromium 3 ion, which is green. So this mixture is going to be green later on. And we have seen this reason when we have seen the difference between primary, secondary, and tertiary alcohol, where we said that primary and secondary alcohol are going to convert acidified potassium dichromate green, while tertiary alcohol is not going to convert, because no oxidation occur in tertiary alcohol, because there is no hydrogen atom bounded to the carbon atom that has the functional group, that is the OH. So now the next one that you need to visualize is oxidation of secondary alcohol. The oxidation of secondary alcohol is going to produce now ketones. So now this oxidation can still take place by with acidified potassium dichromate in this diagram. So when you do that, you see instead form propanone, and propanone is going to evaporate and is going to come in here. So this is what you have. So now let's visualize now the reduction of aldehydes and ketones. So the point to note is that aldehydes, since aldehydes, primary alcohols are oxidized to produce aldehyde, and secondary alcohols are oxidized to produce ketone, they similar things go backward. So it similarly goes round. So aldehydes are going to be instead reduced to produce primary alcohol, and ketones are going to be instead reduced to produce secondary alcohol. So these are the points to note here. So in this case, you have ethanol. When you reduce, so two main molecules are used for their reduction. When you want to reduce it in a solution, that is a hydrophilic solution like water, if you want to dissolve in a polar solvent, you use sodium tetrahydroborate. So you use sodium tetrahydroborate. You use sodium tetrahydroborate when you want to use to reduce this mixture in a solution. But when you want to reduce the mixture inside ether or in a non-polar solvent like ether, you instead use lithium aluminium tetrahydride. You use lithium tetrahydroaluminate. So lithium aluminium tetrahydride, this is sodium boron tetrahydride. This is lithium aluminium tetrahydride, but since this is a complex ion, it's better to call it tetrahydroaluminate, and this is tetrahydroborate. So now these are the different things that you are going to use. So now when you use that, you are going to convert now the ethanol to produce ethanol, which is primary alcohol, and you have propanol converts propan-2, which is secondary alcohol. So now other reaction of aldehydes, you have nucleophilic addition reaction. How does nucleophilic addition reaction occur? The nucleophilic addition reaction occur when you have, so you have this molecule, you see that is now going to produce this molecule. See that this is an addition reaction because there is no loss of another species. So there is no loss of species. All the species which are used in the reagent are combining to produce the product. So this is propanol, and this is 2-hydroxybutane nitride. So this is the molecule at the end. So now let's visualize now the steps for nucleophilic addition. For nucleophilic addition, the first point is that you see that this ring here is a carbonyl functional group. The first thing that is going to occur is that since oxygen is highly electronegative compared to carbon, what happens is that one electron is going to be moving toward oxygen, making this bond to be delta plus on the carbon atom and delta minus on the oxygen. So now the cyanide is now going to the cyanide, which is at the level of HCN, because since the cyanide group is going to be more the cyanide group is going to be more electronegative compared to hydrogen. It's going to pull electron to itself. So when it pulls electron to itself, it produces Cn negative. This Cn negative is going to bond to this carbon atom, which has the delta plus here, and then making oxygen to be completely free. since this oxygen now is completely free, it can now bind to the hydrogen ion, and now it's going to produce the 2-hydroxy nitrate, the molecule which is 2-hydroxy nitrate. So now the next type of reaction that I want us to note is a condensation reaction. So now, how does a condensation reaction occur? In a condensation reaction, it states that any molecule which exists in the form of NH2X, any molecule that exists in a form of NH2X is going to react in a condensation reaction with an aldehyde or a ketone. So this molecule exists as NH2X. And that X means any groups of atom. X means any group of atoms. So in this case, you have NH2 at this position here, and you have X at this other position. This other big ring here is X. So all this is X. So and all this molecule now is going to be called 2,4-dinitrophenylhydrazine. When now you combine, you see that the H2 and the O are going to bind together and are going to be released as H2O, and this is what it makes it to be condensation. You need to know that in condensation reaction, you have addition of two molecules with a loss of in condensation reaction, you have addition of two molecules with a loss of very small molecule which are smaller in molar mass compared to the product, the major product of that reaction. So now you see that water is going to be lost, and then there is double bond here. So this is a condensation reaction forming 2,4-dinitrophenylhydrazone. So now this is this form of reaction is mainly used in a distinction of the carbonyl functional group. So when you have a carbonyl functional group, you can easily use 2,4-dinitrophenyl to distinguish this carbonyl functional group from non-carbonyl functional group compound. So aldehydes and ketones, which have carbonyl functional group, are capable of producing an orange precipitate are capable of producing an orange precipitate when 2,4-dinitrophenylhydrazine is reacted with them, because when they react, they are going to form 2,4-dinitrophenylhydrazone, which is going to be orange in color. Now the next test is going to be trying to distinguish between an aldehyde and a ketone. To distinguish between an aldehyde and a ketone, we need to know that you can use a tolerance reagent and you can use a Filling solution test. So these are the two main tests that you can use in order to distinguish an aldehyde and ketone. But now, what is the point in order for distinction of aldehyde and ketone? The first point is that aldehydes are going to have a hydrogen that is going to be attached directly on the carbon atom, while ketone don't have a hydrogen directly attached to the carbon atom. So now let's see now how it's relevant. We need to know that this hydrogen attached on the carbon with the carbonyl the carbon of the carbonyl carbon atom, this hydrogen has now the capability of doing a reduction. So this is why aldehydes have the capability of reducing other molecules. So since aldehydes are an additional hydrogen on the carbonyl carbon atom, it has the capability of reducing other molecules and being oxidized to produce carboxylic acid, while ketones do not have this hydrogen attached to the carbonyl carbon atom. Thus, it cannot be oxidized to produce primary alcohol. So now when you use a reducing agent, when you use another agent like an oxidizing agent that is going to take electrons from aldehydes and ketone, you see that example in tolerance reagent is silver nitrate in excess ammonia, also called ammoniacal silver nitrate. The silver ion in solution acts as a mild oxidizing agent. When warm, the silver ion will oxidize aldehyde to form carboxylate. So now we have under alkaline condition of carboxylic acid, so all that you see that the aldehydes are going to be converted to produce the carboxylic acid, and now when they are going to produce the carboxylic acid, they are going to affect the silver ion. You need to know that silver ion here is going to be an oxidizing agent, and when it's going to get electron is when it's going to be reduced by the reducing agent, which is aldehyde, is going to form a dark a dark a dark solution of silver. You see that there's going to be a mirror of silver that's going to be formed. So that's the point. So now what's the distinction now with Tollens reaction between aldehydes and ketone? Aldehydes are going to form the dark mirror, the dark silver mirror with Tollens reaction, while ketone do not. And the reason is because aldehydes are reducing agent. So they are reducing agents because of the hydrogen that is going to be that is bounded to the carbonyl functional group, while ketones are non-reducing. Ketones are non-reducing because they have no hydrogen that is bounded to the carbonyl carbon atom. The next thing follow the same principle. Fading solution. In order to distinguish between an aldehyde and ketone using fading solution, for aldehyde, fading solution is going to convert from blue to an orange precipitate. It's going to convert from blue solution to an orange precipitate, because you need to know that one fading solution is made up of copper 2 ion, that is copper 2 sulfate. Since made up of copper 2 sulfate, now you see that what aldehydes are reducing. Since they are reducing, they are going to reduce the copper 2 ion, which is an oxidizing agent, and to form copper 1 ion. And that copper 1 ion now is going to be an orange solution. And also we have the other one, which is orange precipitate. So we have the other one. In cases of ketones, they are non-reducing, so they are not going to cause this conversion. So those are the points. So now the next one is reaction to form triiodomethane. Now you need to know that what for aldehydes and ketone, in order for a reaction to produce a triiodomethane, the group that is necessary is a CH3CO group. The group that is necessary for the production of the triiodomethane is a CH3CO group. So now the point is that when you are going to react any molecule with this group with an alkaline solution of iodine, that is iodine and sodium hydroxide or any other hydroxide, like in this case where you have AlCO CH3, the CH3 must be directly bounded to the carbon atom, to the carbonyl carbon atom. So when you have this molecule, you see that there are two main steps of the reaction. The first step is going to be halogenation. So when you have this, you first have halogenation, the first step with this molecule, and then the second step is going to be hydroxylation. So intermediate is a hydroxylize. The second step is going to be hydroxylation or cleavage. We can also call it cleavage in step 2. So when the cleavage is going to occur via the sodium hydroxide, while the halogenation is going to occur via the iodine, where it's going to bond to everything. Now we have cleavage here, where there's a breakdown into alCOONA, and then there's going to be CH, which is triiodomethane. And this triiodomethane is actually what is called chloroform. So now let's continue with the next point. We have now the testing of the CH3CHOH group. So now in order for you to test for this group is, you see that what's the relation between this group and this group? You see that this group is actually the same with this group, but this is a corresponding alcohol for the formation of this ketone or for this carbonyl compound. So this is a corresponding alcohol for the formation of this carbonyl compound. So if there is an oxidation of this molecule, you are going to produce this. So the testing for this molecule is similar to this molecule with another step which is going to be previous to this step. So now we realize that triiodomethane test can also be used for this identification. So what happens is that you still add alkaline iodine solution. But the first step with this molecule is that the alkyl solution is going to cause an oxidation to this molecule. The oxidation of this molecule is going to produce this this group CH3CO group with a carbonyl functional group. And when you have this group, you can now have this first step inside the formation of triiodomethane methyl. This first step, that is halogenation, and then the second step, which is hydrolysis and cleavage. So now the last part of this tutorial is going to be infrared spectroscopy. We need to know that what the infrared spectroscopy is used in is a spectroscopy where we are going to use infrared, which is part of electromagnetic spectrum. We emit infrared on we target infrared on a medium, a solution. So now, what is the role of this infrared spectroscopy? Infrared spectroscopy is used to identify the different functional groups. As you can see here, you have different functional groups that you can use to identify. You have alcohol, ether, esters, you have aromatic compound, we have amides, ketone, aldehydes, all that. You have alkynes, you have nitriles, you have alkanes, and all that. So if you have a molecule that you don't know the compound, you can identify the functional group of that compound using infrared spectroscopy. But now, how does it function? It functions by the fact that you are going to try to emit infrared light on a certain compound, and then that compound is going to produce a spectrum of absorption of infrared. Example, this is a spectrum of absorption of infrared molecule. You see that when the wavelength of infrared is going to be something like 4000, high absorption of infrared occurs. When the wavelength is reduced to 3500, there is low absorption. When the wavelength is reduced again to 2500, absorption increases. When the wavelength reduces to 2000, absorption increases again. And when it reduces again to something like 1500, it reduces again. So it produces a spectrum, and each spectrum has a particular functional group attached to it. So this is the infrared spectroscopy. So these are different molecules. For alcohol ethers, absorption range is going to be this 1004 to 1300. For aromatic compound, the absorption range like this range where there is most absorption is going to be between 1500 to 1680 per centimeters of wavelength. So these are the different points that you need to put in mind. So when these are the different spectroscopy. So from here we say thanks for your kind attention. This marks the end of aldehydes and ketones tutorial. So let's go to the next tutorial. Thank you.